Hi, Algebra 2. In this lesson, you're going to be working on the natural logarithm or the natural base e, and all of the properties you've already learned for logarithms will still apply. The only difference is what the base is. Here we go. First, we're going to look at where does this natural base e come from? And the first thing we're looking at is the compound interest formula. This is not something that you need to memorize. And it's very similar to our regular old exponential function. P is your initial, just like your A. This is the rate and its growth. If because it's compound interest, you're gaining more money. So it's 1 plus, and this is how you figure out the rate. This is the percent, and then this is how often it's compounded. So how often do you get that each year? And then this, the exponent, it's just like this exponent, except it's how many times it's compounded times the number of years. As the n, or the number of times that the interest is compounded, gets very large, so compounded more and more often, then we say that the interest is continuously compounded. And when we get there, if we graph this out, a compound or continuously compounded interest, the graph would approach this line, which ends up being what we call E. It's 2.718, blah, 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 blah. It's like pi. It goes on forever without repeating. And this is what we call E. This is the graph that we just saw, with E being that asymptote, that line that the graph gets close to but never crosses. And then this is what it looks like if you graph e to the x power. It looks very similar to any exponential function we have. When you start using e in your Desmos calculator, the easiest thing to do is just to use the letter E on the keyboard with the alphabet. And when you do that, you'll see that number 2.718, so on and so forth, pop up. When you graph the function on this slide, e to the power of x minus 2 plus 1, you're going to see that exponential function show up. And if we want to be able to figure out some of these values to fill in our table, I'm just going to make a table here. Oops, duplicating didn't work. I'll take that one away. And now I see a bunch of values that I can then go ahead and graph in my notes. And I'll add a few more values in this table as well. And there we go. So if we have a function f of x equals e to the x, we want to do the inverse of that. That's going to be a logarithm. But when we do a logarithm with a base of e, it's going to be called the natural logarithm. So it's abbreviated as ln rather than just using log base e. So natural logarithms has the same properties as everything else we've done with logarithms. And when you graph it, here you'll see that it is the inverse of that function e to the x power. Before we start working through these examples, I rewrote down the properties of logarithms that we've worked with so far. I've just written them using the natural log instead. So it's the same properties, just writing it as a natural log instead. So all of these should look very, very familiar. The other thing to remember is that the natural log of e is just going to equal 1. And that's because the base of the natural log here is e. We don't write it, just like in logarithms, we don't write it if it's base 10. But the base here is e. And so rewriting this as exponential would be e to the first power equals e. So that's why the natural log of e is just 1. So in A right here, this one is going to go along with this property right here. And we're going to simplify this to just whatever that exponent is, 0.15t. In B, we're going to be using this property and this property. Because the 3 out here is being multiplied, but this property down here is just saying that if e is taken to the power of the natural log of something. So I'm going to take this 3 and I'm going to put it right over here back to its place as an exponent. And then what I have is e to the natural log of x plus 1 to the third power. And again, that's this property right down here. And I can rewrite that as just x plus 1 to the third power. In C, I'm going to simplify these first, again using this property down here. So it'd be 2x plus x, which is just 3x. Here we see the formula for continuously compounded interest. And this is where we see e come in as a number that we're going to be multiplying by to figure out a problem. Zooming in on what this equation is telling us, I call it the PERT equation. P is going to represent your principal or your initial amount. E is just the number E. R is going to be the interest rate as a decimal. So if it's a percent, convert it to a decimal. And then T is your time in years. So in this problem, our initial amount is $500. We're going to multiply that E to the power of, our interest rate is going to be 0.0525, putting that percent as a decimal, times T, which is 40. I use my calculator to evaluate this, and after 40 years, you would have a little over $4,000. We would write this as $4,083.08. Another application, or where you're going to see the number E, is when calculating the half-life of something. So you might hear about this like in chemistry or something like that. The formula is very similar to our PERT continuous interest formula, but the difference is just really the variables that they use here. Here they're going to say in your book that N is the initial amount. That's the same as P. Here's the number E that you're multiplying by. The rate right here is going to be negative in this formula because it's decaying. You're having less of it. And then T is going to be the time in years again. So these are really the same thing. Your book just chose to use different variables for them. Okay, I'm going to write it down as PERT. Remember, it's the same thing. We just know that if it's decay, this R has to be negative. I'm starting by filling in what I know. I know that I'm starting with 1 gram. I know that I'm going to end up with 0.1 grams. I know that E is going to be the number here I'm multiplying by. I don't know how many years it's going to take, and I also don't know the rate, or in this case we call it the decay constant, but I do know it's going to be negative because it's decay, so I'm going to add that negative in there. So I have two things that I don't know, which is not going to help me solve this. So I need to back up and think of a different way to approach this. I do know that the half-life is 24,110 years. So that means if I start with 1 gram, I'm going to have half of a gram, or half of that, in 24,110 years. So now I have just one variable here. I can solve for R, and then I'm going to use that over here to solve for T. To solve this, I'm going to take the natural log of both sides. Just like before we took the logarithm of both sides, we can do that here. And I'm going to end up on this side with the natural log of 1/2 equals, I'm going to use our one of our properties of logarithms to write this as just the exponent. So I have negative R times 24,110. To get R by itself, I'm going to divide both sides by negative 24,110. And I'll use a calculator to evaluate this side of it. When you're looking for the natural log in your calculator, it's under miscellaneous. It's right by your other logarithm functions. I rounded this to 0.000029. So that's going to be my R that I'm going to plug in over here and then now solve for T. We're going to do basically the same process over here. We're going to take the natural log of both sides, and I have natural log of 0.1 equals, over here, this is just going to equal that exponent based on our properties of logarithms. And I'm going to divide both sides. And using my calculator to evaluate this side, I get T to be about 80,000 years. So it's going to take 80,000 years for this to decay from 1 gram to 0.1 grams.